Camera cut me off there for whatever the reason may be. So as the inside becomes more and more negative, right, that's going to slow down the rate that potassium is leaving. Right, because we're developing an electrical driving force, right? Potassium is leaving through its chemical driving force, but as the electrical driving force becomes stronger and stronger, it's going to start pulling potassium backwards. Now, when we think about sodium, sodium is coming in through its chemical driving force. And as the interior becomes more and more negative, because more positively charged ions are leaving than sodium, or than positively charged ions are coming in, now we develop an electrical driving force. What does that mean for sodium? Sodium now has a chemical driving force to come in, but it also has an electrical driving force to come in. So double whammy here, right? Sodium has two forces pulling it in. So this is what's going to happen. As the inside becomes more and more negative, the rate at which potassium leaves slows down. And as the inside becomes more and more negative, the rate at which sodium comes in is going to increase. So potassium is going to start slowing down the rate at which it leaves because the electrical driving force is going to pull it back. And sodium is going to start increasing the rate that it comes in because the extra electrical driving force is going to be pulling it in, as is the chemical driving force. All right, and then eventually what's going to happen? This varies from cell to cell exactly when this is established, but we're going to get to what's called the resting membrane potential. Many cells, it's right around negative 70 millivolts. When we get to negative 70 millivolts, what happens is the inside is negative enough that the rate at which potassium leaves equals the rate at which sodium comes in. Because as the inside became more and more negative, it slowed down the rate that potassium was exiting, and it increased the rate at which sodium came in. And when we get to negative 70 millivolts, we get to the resting membrane potential. The cell rests at negative 70 millivolts because the rate at which potassium leaves equals the rate at which sodium comes in. And now we have the same number of positively charged ions leaving as positively charged ions coming in. If the same number of positively charged ions is leaving as positively charged ions coming in, then the proportion of positive and negatively charged ions on the inside isn't going to change anymore. So the cell rests at negative 70 millivolts. That's how you get to the resting membrane potential with cells. You have to get to the point where the rate at which potassium leaves equals the rate that sodium comes in. The cell's always going to be more permeable to potassium, but as you make the inside more negative, the rate at which potassium leaves equals the rate that sodium comes in due to these changes in chemical and electrical driving forces. And there's one last thing to say here with the resting membrane potential, and that is, this obviously couldn't go on forever, right? This wouldn't make any sense because eventually you're going to get to the point, sorry, let me erase this a little bit. If this just kept going on and on and on, right, all the potassium would leave and all the sodium would eventually come into the cell. And everything would be completely thrown off, right? You'd go from having high sodium on the outside and low sodium on the inside to having it flip-flopped because sodium would just keep coming in, and then eventually you'd have high sodium on the inside and low sodium on the outside. And if potassium kept leaving, then you'd have low potassium on the inside, high potassium on the outside. Wouldn't make absolutely any sense. Okay? So how do you maintain the number of sodium and potassium ions on the inside? Because on the inside we always want potassium to be high and we want sodium to be low, otherwise this whole thing is thrown off. So located throughout the plasma membrane are sodium-potassium pumps, a type of primary active transport. These sodium-potassium pumps use ATP, and what these sodium-potassium pumps do is they take potassium and pump 2 potassium ions in and 3 sodium ions out. So sodium-potassium pumps constantly kick potassium back in and they kick sodium out. Why do you need ATP? Because we're moving sodium and potassium against their concentration gradients. But we have to in order to keep potassium high on the inside and sodium low on the inside. These are going on at all times within most of the cells within your body. Sodium-potassium pumps are one of the most essential primary active pumps that exist in the body. Okay, so we use this, the integral protein uses ATP to move potassium from the outside in. So sodium is moving, I hope I said potassium. We use ATP in order to kick potassium from the outside in, and we're moving potassium from an area of low concentration outside of the cell to an area of high concentration inside of the cell. If you want to move a molecule against its concentration gradient, you need ATP. And the same thing is happening here with sodium, right? We're moving sodium from a low concentration inside of the cell to a high concentration outside of the cell. In order to do that, we need ATP. Okay, so as long as these sodium-potassium pumps keep going, that's going to keep the amount of potassium inside high, right, because we're moving potassium back in, and it's going to keep the amount of sodium on the inside low, right, because it's kicking sodium out. Okay, so the sodium-potassium pumps make sure that potassium on the inside stays high and sodium on the inside stays low, and as long as those concentrations stay the same, this process can continue on indefinitely, and at negative 70 millivolts, we can forever maintain the resting membrane potential.